All right, so one of the things that we need to be able to do is to graph polynomial functions. And you'll remember that a polynomial function is a function that looks something like this. It has a bunch of terms. This one is a 7th degree polynomial, big, long expression, and something that we use a lot in algebra. And we need to graph these things. And I've actually got the graph here of the thing as generated by a computer program. And you can see that thing is complicated, right? And in fact, when we graph polynomial functions, it's very common that we get these roller coaster functions up and down. And so the question is this: is there a way to graph these complicated functions without having to make an entire XY table, which would require many, many X's and Y's, and still get the basic and most important features of the graph? So we want to look at how to do that. Now, we're not going to graph this polynomial in front of you. I just wanted you to see how bad they could get. But we will talk about a couple things. So there are three things that we'll do when we're trying to sketch the graph of a polynomial. And I'm going to illustrate those using this graph. The first thing we're going to do is we're going to figure out how the left and the right ends of the graph behave. Now let me fill this in so you can imagine. Imagine this graph just does this. Okay, so there's our graph. And we're used to graphing these things and usually putting arrows on the end of them, right? Indicating that that graph goes off in those directions forever. Those two places, here and here, are what we're calling the left end behavior and the right end behavior. And really there's only two things that can happen. Either they're going to shoot up towards positive infinity or shoot down towards negative infinity. So the first thing we're going to do in order to sketch these graphs is we're going to figure out real easily where the left and the right behavior, the left and the right ends of the graph go. Do they go to positive infinity or do they go to negative infinity? And there's a real easy way to do that. We're going to use what's called the leading term test to do that. Okay, so that's the first piece of information we're going to find, and it's very easy to find. The second piece of information we're going to find the zeros of the polynomial, which turn out to be the x-intercepts of the graph. Okay, so here on this graph, we're talking about, we're going to locate these points. So remember, you already have the end behavior, the left and the right end behavior. Now you're going to find those, let's see, in this case, 6 points to see and find out where the graph crosses the x-axis. So in reality, you're going to have something like this. You'll know the arm goes up, you'll know this end goes down, and you'll know the graph goes through these points. Now that's almost enough to be able to sketch the graph. We need a little bit more information in order to be able to do that. And so the last thing we'll do after we find the x-intercepts, we're going to find the multiplicity, which is a very simple idea, and we're going to determine and use that multiplicity to determine whether the graph goes through or bounces. Now let me explain what I mean by going through or bounce. So here's a graph, and here's an x-intercept, and here's an x-intercept. The graph could go like this. In this case, we say the graph goes through the x-axis, right? I mean, it crosses over. Here is what we refer to as a bounce. This is what I refer to as a bounce. So those are the only two things that can happen at an x-intercept. Either the graph will go through it or bounce it, okay, or bounce on that. Now, so that's the third piece of information. Combine those, take all three of those pieces of information, and you'll be able to sketch the graph. Okay, so let's see that in action here. We're going to do it with this polynomial, which is much simpler. Okay, now the first thing we're going to do is the leading term test. So let's write this down. The leading term test is what we want to look at first, and it's the first thing we'll do. and its purpose is to find or to determine the left and right end behavior of the graph. Where do the arrows go? Okay, that's all it does, but it's very simple to do. We're going to look at the polynomial, and we're going to look at two things. We're going to look at, number one, the degree of the polynomial. So let's take our example here, x cubed plus 3x squared minus 9x minus 27. Remember what the degree of a polynomial is. It's the largest exponent. So in this case, this is a third degree polynomial. Okay, so the degree will be either an even number or an odd number. Those are the two classifications. So in this case, it's an odd number. The degree is 3. Okay, so that's one piece of information we're going to look at. The other piece of information we're going to look at is the leading coefficient. And so that's the coefficient on the leading term. Now, it looks like I'm not highlighting anything there, but remember that coefficient is a 1. There's a little transparent 1. So the leading coefficient in this case is 1. And what we're interested in is not whether it's positive or even or odd, but we're interested in whether it's a positive or a negative number. Okay, so those give us the 4 categories. And so here's what's going to happen. And you can think about this using the graphs that you're familiar with. If I've got an even degree and a positive leading coefficient, the arms of the graph are going to go up, both go up like that. The classic example is x squared, right? Think about the x squared graph. Isn't that what the arms do? X squared, it's an even degree and a positive leading coefficient. Well, for even and negative, arms are just going to flip. Again, think negative x squared. Right? Think what happens when you put a negative in front of a function. It reflects it around the x-axis, so they're both going to be going down. Finally, the odd positive. Now this one, the left arm is going, I keep calling these arms, the left end is going down and the right end is going up. Think about x cubed as the example, as the most basic and simple example of that kind of function. And then finally, we can do it the other way. If it's an odd and negative, like negative x cubed, then the left end is going up to positive infinity, and the right end is going down to negative infinity. Now, there's some official notation that we talk about with this. For instance, if I want to say, if I want to refer to, say, this right here, that arm, I could write this: the limit as x goes to infinity of the function is negative infinity. So what that's saying is that as our x's go to infinity, right? So as we, on the graph, as our x's get bigger, as they go this way, right? As the x's go to infinity, the y values, the things you get out of the function, go to negative infinity. And you can see that right there. That's some pretty high-level notation. We're not going to focus on that in this video. I just want to show you how to use the leading term test. Okay, so with that in mind, let's return to our function and apply the leading term test. Okay, so as you can see here, this particular function has, like we said, an odd degree and a positive leading coefficient. So we know, and let's start to sketch its graph right here. We know that according to the leading term test, this left end behavior will go down and this right end will go to up or go to positive infinity. Now, we don't know what's happening in here, right? That's important to remember. We have to figure that out. But we do know what the arms of the graph, the ends of the graph are doing. Okay, so that's number 1 in our list right back here. Use the leading term test, and that will get you this much of the graph. Now, it doesn't look like very much, but it will work together. So let's go to the second thing, which is to find the zeros. Now, we've done this before, so we know how to do this. So we want to find the zeros of f of x. So what that means is we want to take f of x, and we're trying to figure out when does it equal 0. And since that's a polynomial equation, the method we use to solve polynomial equations, most polynomials, is to factor. And this one, since it has 4 terms, we might try to factor by grouping first. And it looks like grouping is going to work. Factor out the common x plus 3 and that x squared minus 9, which we'll go ahead and add right in here as x plus 3, and then x squared minus 9 is the difference of squares, factors in x plus 3, x minus 3 equals 0. And so that's going to yield the 3 zeros, negative 3, negative 3, and 3. Now, you might be wondering why I wrote down negative 3 twice. I'll talk about that later. But what we have found is number 2, right? The number 2 part of our process. We found the zeros, which we know are x-intercepts. So let's put them on the graph. We know the graph has to go through or touch that point. And we know the graph has to go through or touch that point. Okay, so we're starting to fill in this middle area. Okay, to finish it off, we're going to do step 3, which is to determine the multiplicity. Okay, so the multiplicity of a 0 is simply how many times the 0 shows up in this list. How many times is it a 0 of the function? Or another way you could think about it is how many times we know that minus 3 was a 0 because we had this factor, x plus 3. How many times does that factor show up? Well, that's the multiplicity. So minus 3 has a multiplicity of 2, and 3 has a multiplicity of 1 because, look, 3 only shows up, the factor related to x equals 3, which is x minus 3, only shows up once. Okay, so here's the rule. And let's write it like this. If the multiplicity is odd, then the graph goes through that 0. Okay, so if the multiplicity is 1, 3, 5, or 7, the graph goes through. And then the second rule is if the multiplicity is even, then the graph bounces. Okay, so look, we've got one even multiplicity, which is minus 3, and one odd multiplicity, which is 3. So our graph we know is going to bounce off minus 3. I'm sorry, bounce off minus 3, but it's going to go through 3. All right, so that means our graph, which we know has to start down here, it's going to come up and bounce. So it just touches, it doesn't go through, and then it's going to have to turn a U-turn to get back and go through and end up there. Okay, and there we have it. We've sketched that graph. Now I know this has seemed like a long process, but once you've done it a couple times, you'll see that these steps don't really take a lot of work. The hardest one is step number 2. Now the second issue you might be wondering is how far down does my graph go? I mean, should it go like this, or should it go like this, or what? How much detail do you need? Well, for these sketches, we're not really worried about how far down it goes. We're worried that you have the shape, the bounce, and they go through, and the ends end up in the same place. If you want the detail, then what you would do is you'd make a quick little XY table. You'd say maybe just plug in one point and say, all right, let's let x equal 0. And so if you plug in 0, you know that y will be negative 27. So this point probably doesn't look like it here. This point will be negative 27, right? And it may not be the minimum of that little valley there, because we don't have that level of detail. And quite frankly, we're not terribly interested in that kind of detail for this analysis. We just want the general shape. So that's how you sketch the graph of any polynomial. You use those 3 steps, and that'll give you the general shape.